Hey everybody, in this video we're talking about fluid pressure. We defined pressure in fact in a prior video. In this one we're going to see how it applies more specifically to liquids and gases. Sorry if this video is a little longer than my average runtime. We have a handful of things we need to get done. First, what is the origin of this fluid pressure? There's an equation for it. You are of course familiar with air, but that air exerts a pressure we call atmospheric pressure. What's going on there? And then there's actually two different ways to measure pressure, or that you might see it measured. And so we need to understand that difference between absolute pressure measurements and gauge pressure measurements, okay? First up, let's understand the origin and nature of this fluid pressure. What do I mean by that? You're already familiar with this idea in several ways. For example, in like a carbonated soda, that soda is pressurized, or maybe you kind of hear the sound when you uncap a bottle of soda because there is pressure in that container. Even like swimming in the ocean or in a pool, maybe you're familiar with this idea that as you go deeper in, there's more pressure on you. Or if you go flying in an airplane, the air itself has pressure, and if you go in an airplane, you might notice that pressure change, especially say in your ears. So what's going on? This first bullet point is kind of highlighting the key idea. Even though in AP Physics 1, we are mostly dealing with objects on our scale, like human scale, blocks, even like a flow of water through a pipe, the origin of pressure is really going to require us to do a quick detour. We're dealing with atoms and molecules and the motion of those atoms and molecules. Atoms and molecules which make up a fluid, say a liquid or a gas. If you remember, in fluids, in liquids and gases, those particles, those atoms and molecules, they are not tightly bound together like they are in solids. In liquids and gases, those particles can move around much more easily. And what that means is that those particles can move and collide with one another. They can collide with their own particles. They can also hit the sides of the containers that they are in. And team, I don't know if you remember the impulse equation. If this little particle is slamming into the side of the container, it is feeling a change in momentum, which means there is a force applied on it. And even by Newton's third law, if there's a force on the particle, there must be a force actually also on the container itself. So these particles are colliding with each other, but they're also colliding with things around them, like the container of this soda bottle that is applying force. And it's that force that is acting on, let's say, the sides of the soda container, which are exerting a pressure, that force over a given area, okay? Now, team, pressure acts in all directions. And that's a little weird because, again, in the rest of this class, we're familiar with this idea of like, if I apply a force to the left, the object is only feeling that leftward force. It's going to feel an acceleration perchance toward the left. But because fluids do not have strong lattices, they're not strongly bound together. In fact, when you apply a force, like imagine punching water or splashing water, yeah, you're maybe initially applying a specific force in a specific direction, but those water molecules, they're all moving and sliding past each other all loosey-goosey. Automatically, seemingly, that particles, or those particles, are acting and applying and moving in all different directions. So pressure does not really act in one single direction. There's some fancy or funny YouTube videos where people are compressing different material. I just have a clip here of compressing some crayons. This compressor here is applying a force that is initially downward, but when it's pressed onto the crayons, all that pressure makes that material move in all different directions at once. And so, because there's little holes in this little press right here, the crayons actually don't just move down, they press up and out in all directions. That is also true for liquids and gases. So everybody, it's maybe a little weird, but pressure from the air, pressure from the water, it's not acting in one direction. It's really acting in all directions at once. Because again, even if you apply one like initial force one way, those particles can all collide and slam in and slide in different directions. There's like glancing blows happening all the time and all at once. So pressure acts in all different directions, okay? Now, let's get into an equation that describes and that defines how much pressure there is from a fluid, okay? It's known as the fluid pressure equation. And to do that, team, it's a little weird, okay? I have drawn here a beaker of water. So I have this container of water. Obviously, it is filled with water molecules. I'm going to look at one specific area. I kind of have this circular area right here, all right? And we're going to call this area location P, and we're going to think about the pressure that is acting at this location right here. First, everybody, a couple of things to help us out, all right? We're going to use an equation for pressure, and remember, pressure is equal to force divided by area. Now, the pressure from a liquid actually comes from the fact that here on planet Earth, water and air, they have weight associated with them. And we learned the equation for weight a while ago. Weight is based on mass times g. Team, instead of using mass when we're dealing with fluids, we often want to deal with the symbol or the fundamental topic of density. Why? Mass is going to be based on how much of the liquid you're dealing with. Density is a constant for a particular liquid. Like water has a specific and constant density, okay? If I had some other liquid, it has a constant density. So remember everybody, density is defined as mass divided by volume. Or I could rewrite this if I wanted to. If I solve this for m, the mass is equal to the density multiplied by the volume. And why might we do that? Because that means I could rewrite weight. The weight of a liquid, that is going to be based on, instead of m, I'm going to be doing the density times the volume and multiplied by g. It's still based on that gravitational acceleration, okay? So that is another way we could represent the weight of a fluid. All right, I moved on to another slide, and obviously you've seen some changes. First, I just kind of copied down those couple of equations we saw in the last slide, and now I'm adding a little bit to my diagram. So this was the first one, and let's just add a little bit of detail. I'm focusing on the water because I want to look at the pressure that's located right in this spot here, this kind of circle, all right? Well, if we imagine the fact that, of course, here on Earth there is weight. Weight is a force that pulls things down. At this location, there are water molecules directly above it. There's a water molecule right there, and that water molecule is feeling a downward force of weight equal to m times g, right? There's also this water molecule, and this one, and this one, and this one, and this one, and this one. There are water molecules above this location that I kind of circled that are acting or exerting downward forces. Now, there's also water molecules over here, of course, but weight is only acting down. So the fact that there's a water molecule over here, I'm actually able to ignore, because whatever downward force it's feeling, it's not directly applying that downward force on this given area. That's why I made this second diagram. I've now, even though there's no actual like cylinder in this larger container of water, I'm focusing on this imaginary column of water that is exactly above this spot. It is this water here and the weight of this water here that is going to be applying forces, or a overall amount of force, on this location. So I'm looking at this column, and this column of water has, let's just call it a height of h. Let's say this column has a cross-sectional area of a. This looks like a cylindrical column, okay, meaning like different from like a square pillar or something. But to be honest, it doesn't matter whether it's a circle that's then continued downward, or a square or a rectangle. We're just going to call that its area and its height. So what is the volume of this cylinder or this column that I made? Well, the volume, maybe you have to remember a little bit of geometry, it's going to be based on the area and how high up that area extends. That volume is going to be equal to A times H. That's what's equal to V, not velocity, volume. So the volume is equal to A times H. Okay, we're getting closer to being able to define our equation. Okay, everybody, another slide again. I have that diagram right there. I have those equations, including the new one. The volume is equal to the cross-sectional area times H. Let's derive the equation for fluid pressure. This is the pressure just from the fact that there is water above any location I'm looking at, and that water is feeling a downward force because of planet Earth, because of Earth's gravity. So let's remember, pressure, that's equal to force divided by area. That was our original definition, all right? The force that we're dealing with, that's equal to the weight that is directly above whatever location I chose. And team, we're keeping this super vague and general, and that way I can apply it whether this location is maybe closer up here, further down below. The pressure in a liquid is based on a force. The only overall force that is acting at this location is the weight of the water above. If you're thinking like, what about like forces from the side? Like, to be fair, you're right, particles are hitting from the side, but those are gonna on average cancel each other out. If I have water particles hitting on this way to the left, and then water particles also hitting on this way to the right, those are canceling. But I have a weight force. Earth is pulling water downward. So any fluid, any liquid or gas above is applying a downward force. There is no fundamental force on Earth that's saying like there has to be some opposite force upwards. So that's not there. So that's why we're focusing on this downward force, all right? So again, pressure is equal to force over area. That's mg divided by A. We don't want to use m, or at least maybe I should just say classically we don't use m. So I'm going to plug in, instead of m, the density of the liquid times the volume. There's still G here. There's still A right here. I'm going to plug in again. So now I'm going to go right below, okay? I still have density. What's the volume? I'm going to flip over to red. The volume is equal to the cross-sectional area times the height. I'm going to go back to yellow. I should do a better job color coordinating. Times G divided by A. And everybody, what do you notice? Well, there's also, in addition to the A below, there's an A up top. So that means I'm going to go back to blue for my final equation. The pressure is equal to, I have rho Team, the A is canceled and it's H times G. I'm just gonna flip the order I'm writing these. In math, A times B is the same as B times A. And just classically, it's written in this way. The pressure from a fluid, that is equal to the density of the fluid multiplied by G multiplied by H. Okay, let me just go like that. So rho is the density, G is the gravitational constant. That is still 9.8. That hasn't changed. And H is the height, how much liquid is, or how much fluid more specifically, is above it. That is our equation for the density of a fluid. Okay, with that in mind, everybody, let's look at an example. I have 3 different containers right here. They all have water at some level, and we're always looking at one specific spot, like here and here and here. It's asking, or the idea of this scenario, of this diagram, is suggesting what is the pressure, or how do the pressures compare at these 3 different locations. And if you read my bullet point, you know the idea. Pressure is based not on the shape of the container. Pressure for a liquid or a gas does not depend on how much water is over here or over here. It doesn't depend on whether or not the shape of the container is changing as we go down or across. All the fluid pressure depends on is the density, and for water, if all 3 of these is water, that's the same for all 3. For G, and G is 9.8, and that's the same for all 3. And H, that's the height. And in these 3 diagrams, that's the same in all 3. So everybody, in all 3 of these containers, they have the same amount of pressure at this location. Why? Because they have the same amount of water above. And again, it's the force of gravity on planet Earth pulling fluids down. That is what is causing the pressure in the first place, and that is only based on the amount of water that is above it. So the fluid pressure, it's a little bit of an unintuitive fact. It's not based on how much water is left or right of a given spot. It only depends on how much water is above. All 3 of these diagrams of these beakers, they are feeling the same amount of pressure at a given depth, all right? Okay, now we have that the equation is finished and derived and under our belt. Let's look at some examples. And there's no more math in this video, so that's nice. We have 2 more sections. Part C is atmospheric pressure. We're not deriving any more equations, but atmosphere, the air, it is a fluid, so that means we have the equation for the pressure of a fluid, the density times G times H. Air has a certain density. Here on planet Earth, it's 9.8 for G, and based on the height, there is a certain amount of air pressure. It's all the exact same rationale as the derivation before. It's often easier to think of it as water when we start and when we derive the equation, but air is also a fluid, so this is just as applicable, all right? Air exerts pressure on all objects. Air is exerting a pressure on you. There's kind of this misconception, or like there's this fun fact that isn't quite as fun as it sounds. People say, oh, you know, the air around you is applying pounds and pounds of pressure on you on every square inch. So that means you are ripped and you are able to support this huge amount of weight from the air. And that is kind of true. The air has a lot of weight above us, and that weight is pressing down on you. But team, remember, air is applying pressure in all directions. So it's not really true to think about the air as simply pressing down on you with a large amount of force. There is a large amount of force, but in a given area, that's being balanced. In your lungs, there is also that air pressure pushing outwards. You have cavities in your own body, like your sinus cavity. That is a space in your skull. It has air in it. That's at the same pressure. So yeah, I mean, the air is applying forces on you over every given square inch, but it's not just on like your shoulders. It's not just on your head. It's in all different directions for the reasons we talked about earlier. It's even acting on the inside. So those things are all balancing. It's kind of like a Newton's second law. All those forces are balancing on all sides. So there's not really this overall crushing force that you are able to overcome, not at least in a large or general scale. Now, this atmospheric pressure, it does have a certain amount. It's 14.7 pounds for every square inch. So every square inch on the ground or on your shoulders or on your head, there is 14 pounds of air just sitting on you, or that's applying a force on you. We could write that in terms of units that we use more often in our physics class. That's 1.013 times 10 to the 5th newtons per square meter. Remember, this is also a Pascal, so about 1 times 10 to the 5th pascals. This is also, frankly, given its own kind of unit. And I'm sorry, there's kind of a lot of units for pressure. We're not going to use all the ones that you might come across, but there are a handful. We've seen pascals. For the atmosphere, we also or often just call that 1 atmosphere of pressure. At sea level, there is 1 atmosphere's worth of air pressure all around you. And if you go higher up, there's less pressure. Does that make sense? It should, because if you're higher up, there's less air with weight acting down on you. Remember, the origin of air pressure and all fluid pressure fundamentally is gravity pulling that fluid downward. So if you're higher up, there's just less air that's above you. If there's less air that's above you, there's going to be less force acting down, less weight from that air, and therefore less pressure. So that's why pressure goes up with atmosphere, because there's just fewer amounts of air particles that have weight that are above you acting downward. All right, everybody, we are on the last part of this video, all right? Gauge pressure, and then we're going to touch upon something known as absolute pressure, see atmospheric pressure again. Team, after all I just said about how the atmosphere is applying a pressure, maybe you thought of this, maybe you didn't. If you have a bicycle pump or like an air pressure gauge for your car tires, maybe you recognize that those all start at 0. If you have a bicycle pump, it has 0 if it's not connected to the tire, or if like the tire is totally flat. What's going on there if we have atmospheric pressure from just the air around us? Well, team, those objects are measuring what's known as gauge pressure. Gauge pressure is additional pressure, or maybe the lack of additional pressure, besides air itself. Remember, we're always surrounded by air. That's like a constant. So one way we could measure pressure is just like, oh, okay, we know there's air pressure, but let's not always have to include that. Let's be looking at the additional, the on top of pressure. That's what gauge pressure is. When you are pumping up your bicycle, what you're doing is you are adding pressure in addition to the pressure from the air. So that's what gauge pressure is. It's often a way that we'll measure pressure, which just kind of means it's the amount in addition to the pressure that's already around us, all right? So that's what gauge pressure is. Now, atmospheric pressure is, of course, what's all around us. Gauge pressure is what's looking at what is in addition to that atmospheric pressure, which brings me to my last term for this video, which is absolute pressure. Absolute pressure is the overall pressure, including that from the atmosphere and including that from whatever other amount. Think of a bottle of soda. The bottle of soda is feeling pressure from just the air around it. There is also that added pressure because sodas are carbonated. They have pressurized additional gases inserted into the liquid to give it that carbonation, all right? So there's kind of this diagram that I like. I didn't make this. It's almost like a graph. They didn't label it as a graph. In outer space, where there are no significant air particles at all, the pressure is 0. There are literally no, or essentially no, particles or molecules moving around. So basically there are no collisions, so there's no pressure from liquids and gases. There are no liquids and gases in outer space, really, all right? So the very least amount of pressure you could have is known as a vacuum, absolute 0 pressure, okay? Here on Earth, there is atmospheric pressure, all right? That's what we all experience. And what we call gauge pressure is, again, what's in addition to that atmospheric. So absolute pressure is just the overall total amount of pressure when you want to include everything. Team, I'm sorry, for AP Physics 1, you might be given values, or you might be asked to solve for absolute pressure. That might be given in a problem. It might say the absolute pressure in this container is blank. It also might say that the gauge pressure is blank, okay? That doesn't necessarily always mean you need to add or subtract the atmosphere. It kind of depends, but just know, there's two common ways to measure pressure, whether you're including the atmosphere or just kind of ignoring it. All right, so be aware of that. They'll have to tell you. They'll have to say, oh, the number we're referring to is the absolute pressure, or the number is the gauge pressure. Man, this video is long enough. Just the last thing I want to touch upon real quick is, obviously, we have pressure from the air. Well, when you're going swimming in water, whether that's from a pool or in the ocean, there's still that air pressure that's acting on you. Even when you're underwater, there's still air that's directly above you, and that means the Earth is pulling down on that air, and that's going to exert a force over every square inch of you. But water is this additional fluid. So when you are diving, let's say, you might feel that pressure in your ears because, once again, just like when we saw our original derivation, there is water that's above you. So this diver is experiencing both the pressure from the air and this additional weight of water that's pressing down upon them. So it all just kind of builds up. Why? Because, again, this pressure is from the force of gravity. Weight from the air plus the weight from the water that's above you, that is all applying additional force. And because those water molecules, even though they are maybe initially feeling a force from upwards down upon them, because they can slide and collide and have glancing blows, that pressure is, again, in all different directions, okay? Anyway, man, thanks a lot for watching this video. We're going over a lot, but that's the core information for fluid pressure. Thanks a lot for watching.